Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures in random signal theory. We are still in chapter 2, basic probabilities. Last time we talked about the definition of the random experiment. It's an experiment that if you do, the outcome is uncertain, and we defined the sample space, which is the set of all possible outcomes of a random experiment. And today we are continuing our discussion, and we would like to define an event. Formally speaking, an event is a subset of the sample space of a random experiment. We know that the random experiment is an experiment that if you do, it might give you different outcomes. The outcome is uncertain. However, we know the sample space of the random experiment, which is the set that contains all possible outcomes of the experiment. Now, any part or subset of the sample space is called an event. Usually, an event has a meaning as well. It basically identifies a case of interest. So that's why I thought the best way to proceed is to use my own notes here and a motivating example. Let me start with one of the experiments that we talked about last time. The experiment is we toss two coins and we observe the outcome. So we have two coins, we toss them, and we simply observe the outcome of both coins. What was the sample space of this experiment? It had heads, 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 tails, tails, heads, and tails, tails. These four possible outcomes define our sample space of the random experiment of tossing two coins and observing the outcome. Now let's define an event, a certain event that might happen if you do this, if you do this experiment. Now, let's say we have the event of obtaining at least one head. Let's call this event E. So we just give it another letter. S stands for the sample space, which contains all possible outcomes. And then we define a certain event of interest, a certain case of interest. Let's give it the letter E. And we say, this is just an example. We could have some other events as I try to proceed. This event E is defined as the event of obtaining at least one head. At least means one or more, one or two in this context. So we do the experiment, you toss both coins, and we know that the sample space contains four possible outcomes. And now let's define the event E of obtaining at least one head. At least one means one or more, in this case, one or two. How can we express this event? What are the outcomes of the sample space that are part of this event? Heads, heads. If we have two heads, uh, was the event satisfied? Do we have at least one head? Yes, of course. If we have two, it means we have at least one. So heads, heads is part of the event. Heads, tails, and tails, heads, these two outcomes are also part of the event because for each one of these outcomes, we have one head. Okay, what about tails, tails? Is it part of the event? It's not part of the event. So imagine in the context of the experiment, you toss the coins and then you're not lucky, you get tails, tails. Is this event satisfied? Can we say that you have obtained at least one head? Have you obtained one head or two heads? No, you got tails, tails, so you have zero heads, which means this tails, tails is not part of the event. So simply speaking, the sample space contains all outcomes: heads, 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 tails, tails, heads, and tails, tails. The event of obtaining at least one head can be expressed as heads, 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 tails, and tails, heads. So these three outcomes identify the event. Have you noticed that this event is a subset of the sample space? So this event contains the first three outcomes of the sample space. We say the event is a subset of the sample space. Let's look at some other examples. Let's define E1 to be the event of obtaining exactly two tails. Obviously, E1 contains only tails, tails. It's exactly two, no at least, no at most, exactly two tails. So E1 is tails, tails. So this outcome here, the last outcome, that's the only outcome in our event. Let's define another event. E2 is the event of obtaining three heads. If we do this experiment, we are tossing two coins. Can we obtain three heads? We cannot obtain three heads. So there is nothing here with three heads, nothing in the sample space with three heads. So our event E2 is empty. It does not have anything. It is an empty set. Another name for the empty set is the null set. This is a zero letter with a line. We call it the null set. So this event is empty. As you notice, the event, again, if you go to the formal definition, the event is a subset of a sample space. If this is our sample space, any subset could be an event. The extreme case is the empty set, so the empty set is also a subset of this. Another extreme is if the event is exactly the same as the sample space, so the event contains everything, then basically it is the sample space itself. Imagine here, listen to me, I don't have it written. Event E3 is defined as the event of obtaining at most two heads or less, at most two heads. What does that mean? It means two heads or one head or none, which means all these outcomes are in our event. So E3 would contain heads, tails, heads, and tails, which is the same as the sample space. So this is an extreme case as well. And everything in between, a subset of the sample space, can also be an event. So this is the meaning of the event. Now let's move to the next topic here. We have noticed from the beginning that the sample space is the set. Let's put under set a couple of lines. The sample space is the set that contains all possible outcomes of a random experiment. The event is a subset of the sample space. So we're talking about sets here. We have a random experiment. The set of all possible outcomes is a set that we call the sample space, and the event is a subset of the sample space as well. So it's also a set. So we're dealing with sets. So that's why it's a good idea to revise. Basically, let's try to remember together the basic set operations. What are the operations that we can do on sets? We have the union, the intersection, the complement. You all know that. And let's review this concept basically. And I thought also the best way to proceed is using my own notes. And if we represent the sets or events graphically, it's really easy. By the way, a graphical representation of sets like this is set A, this is set B, is called a Venn diagram. Let's have a peek here. We call it a Venn diagram. So if we just represent a set using a circle, we call it a Venn diagram. So we have a random experiment. In our background, we know that there is some random experiment that has a sample space. Here, this big box is the sample space, which is the set that contains all possible outcomes. And then we have two events, two subsets of the sample space, event A and event B. What is A intersection B? This symbol here, it goes up, it's called the intersection. Intersection means and. The best way to understand it, the best way to imagine it, is the word and in English. If we say A intersection B, we mean what are the outcomes or elements which are in A and in B at the same time. In A and in B at the same time, which means the intersection here. These outcomes belong to A and they belong to B at the same time, so the intersection A intersection B basically is this. Right. What is the next operation that we can do on sets or on events? The union. A union B, so the symbol goes down here. This means union. And again, the best way to understand it is the word or in English. A union B means what are the outcomes that belong to A or belong to B. Belong to A or belong to B. So if this is A and this is B, then everything together is the union. Everything together. So if it belongs to A alone, or if it belongs to B alone, or if it's in the intersection, if it belongs to both, it means this is the union. Everything in A or in B, this is the union. Now the third set operation here, the third set operation is the complement. Let me stick to the same setup. So we have a sample space representing all possible outcomes of a random experiment, and we have event A and we have event B. However, we don't care about B here. We just want to get A complement. This is a prime here or a dash. We can read A complement. What is A complement? A complement means not, again. So the intersection is an and, the union is an or, complement is a not. We mean what does not, what are the outcomes or elements not in A? Everything outside A. So do you see these green lines here? Everything outside A, even if they are in B, everything outside A, this is A complement. Although we have three basic set operations, intersection, union, and complement, I'll add a fourth one. It comes in handy. It's also nice and important. We call it the set difference. It looks like a minus, but it's not a numeric minus. We're not really subtracting numbers. A is a set and B is a set. If we say A minus B, we mean all elements in A but not in B. All elements in A but not in B. We can translate it even if you listen to me talking in plain English. A intersection B complement. What is in A and not in B? What is in A and not in B? We call it the set difference. We can also call it the relative complement, not just the complement outside A here. We mean outside B, but included in A as well. So it's again, let me backtrack. The best way to understand this is the notion of the set difference, A minus B here. So again, if this is event A, and this is event B, both of them are in a sample space. If we say A minus B, the set difference, A and not B, A and not B. What is in A but not in B? It means everything purely in A. Do you see the green lines? The green lines means everything in A pure, not in B. So basically, A minus B contains everything in A, but without this intersection part. Without this intersection part, this is the meaning of A minus B, the set difference. Likewise, I think it's easy for you to extend to B minus A. What would be B minus A? It's everything here. It's everything here in this part that I'm trying to highlight. Here, everything in B, so B without A. Everything in B, but without this intersection, which contain the outcome that belong to A as well. Now, we have some examples. This would be the last topic in this video, but we just have some examples. So here in this example, we have an experiment with the following sample space. So the experiment itself is not given. We don't care about the meaning of the experiment, but we have an experiment with sample space S, which contains YY, YN, NY, and NN. So this could be something like the experiment of measuring the two wires. And then we check if they conform to specifications or not. So yes, yes, both conform. Yes, no, first one conform and the second one does not. No, yes, first one not conforming and second one conforms. No, no, both do not conform to specifications. Just to understand the meaning of this. However, to solve the problem, that's the only thing we need here, that the sample space contains these four outcomes. Okay, now the problem itself defines some events. E1, event E1 is defined as YY, YN, and NY. E2 is defined as no, no only. That's the only outcome in E2. E3 is empty, so it's an empty set. E4 is S itself, which is the same as the sample space. So E4 is the whole sample space. And finally, E5. E5 is YN, NY, and NN. Basically, the exercise here is to find, first of all, what is E1 union E5? What is E1 union E5? Let's have a look at E1 again. This was E1. YY, YN, NY. What was E5? E5, YN, NY, NN. What was the meaning of the union again? The union is the set that contains everything in E1 or in E5. So if it's in E1 or in E5 or in both, it's part of the union. Let's check. YY is in E1, so it's in the union for sure. It's in the union for sure. YN and NY are also in the union. Now let me check the elements in E5. YN has been counted already. NY has been counted already. And then NN is new. So as long as it is in E5, it's also part of the union. So what is E1 union E5? It is simply YY, YN, NY, and NN as well. So it is just the sample space. So that's why we say E1 union E5 is the sample space, because it is the same as the sample space. Let's get the intersection between E1 and E5. Intersection means contained in E1 and in E5 at the same time. What is common between the two? YY. Is it in E1? But it's not in E5. So YY is not in the intersection. YN is in both. It's in the intersection, but we put it only once. NY also belongs to both. It's in the intersection as well. Let me continue here. NN, it's only in E5. It's not in E1, so it's not in the intersection. So the intersection between E1 and E5, E1 intersection E5 is simply YN and Y. A complement example. What is E1 complement? E1 complement means what are the outcomes not in E1? More precisely, what are the outcomes in the sample space? We always have a sample space in our background, even in these pictures. We have a sample space, and A and B are events in the sample space. So what belongs to the sample space but not to E1? What was E1 again? YY, YN, NY. So what is the only remaining outcome in the sample space? NN. So E1 complement is NN. So this is the example, basically. So what you see here is the example. We define a sample space. We define E1, E2, E3, E4, and E5, and we are A, B, C. We are getting a union, an intersection, a complement, and the final answer is here. This S, this set here, yn, comma, ny, and finally the set nn. These are the answers to the questions that we're asking. Now, another definition here. When are two events called mutually exclusive? When are two events, E1 and E2, when are they called mutually exclusive if the intersection is an empty set? In my examples that you have seen here, we have A and B. There is always an intersection. So there is always something common between the two because there is an intersection. In all examples, here is an intersection, we have an intersection, here we have an intersection. However, what if by chance A and B look like that? So this is again my own notes here that illustrates the idea of mutually exclusive. Imagine that we have a random experiment with a sample space S. So this big box represents the set of all possible outcomes that we call the sample space. We have two events, A and B, that don't intersect. If you try to get the intersection, there is nothing in common between them. So A intersection B is the empty set, is the null set. If the intersection between A and B is empty, then we call A and B mutually exclusive events. So basically, mutually exclusive events are events that have nothing in common. Since they have nothing in common, it means that these events cannot happen at the same time. So if event A happens, event B cannot happen, and so on. Perhaps let me try to mention an example here in terms of our motivating example. We're tossing two coins and we observe the outcome. So our sample space contains all possible outcomes from heads, heads until tails, tails. We defined an event E, which is the event of obtaining at least one head. The event of obtaining at least one head. Heads, 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 tails, tails, tails. Let's define another event and call it E1, the event of obtaining exactly two tails, which means E1 contains only TT. Let me ask you the following. What is the intersection between E and E1? What is E1, what is E intersection E1? Is there anything in common between them? Here we have HH, HTTH, and here we have TT. Is there anything in common? There is nothing in common. So the intersection between E and E1 is empty. The intersection between them is empty. So according to the definition that we have just finished, we say that E and E1 are mutually exclusive. Now, in terms of the meaning of this, what was E again? E was the event of obtaining at least one head. The event that you get one or more heads, one or two heads. E1 was the event of obtaining exactly two tails. Now imagine that you toss your coins. You toss both coins and then you observe the outcome. Can these events be satisfied at the same time? I think it's obvious no. Either this will happen. If you get any one of these outcomes, it means event E is satisfied. But if you get tails, tails, it means event E1 is satisfied. So it is impossible. It is impossible that if you toss the coins, event E and event E1 get satisfied at the same time. These are mutually exclusive events. Let me proceed. Mutually exclusive event. I just used the terms A and B. We can also use E1 and E2. It does not matter. These are just symbols that represent event, that denote events. So E1 and E2, if the intersection is empty, we say that E1 and E2 are mutually exclusive events. Let me try to give you another example. Imagine that you take this course. And if you take a course, what are the possible outcomes in terms of the grades? The possible outcomes are A, B plus and B, C plus and C, D plus and D, or F. So we have 8 outcomes. After you finish the course, what you get is one of these 8 outcomes. That's the sample space. So the sample space of the grades that you obtain after you finish the course contains A, B, B plus, and so on until F. These are the outcomes. Now let me define two events. You take the course, you're an excellent student, you are interested in getting an A, but if you think if you get a B plus, it's also fine with you, let's define the event E1 to be the event of obtaining B plus or better, the event of obtaining at least a B plus. So that event contains A and B plus. Now, let's imagine you are scared of getting something bad in the course. So you're scared of getting a D plus or a D or an F. Let's put these in another event E2. In another event E2. So E2 contains D, D plus, and F. Now, imagine that you take this course. You take the final exam and the result is online. You check your result, you find your grade. You find your grade. Is it possible that E1 and E2 are satisfied at the same time? You have a grade. You have a grade. So let's say you got a B plus. This means that E1 is satisfied. This event is satisfied, but the other event is not satisfied. لا قدر الله, you check your grade, you find it's a D plus. It means that the second event, E2, is satisfied, but E1 is not satisfied. So these two events cannot happen at the same time. It's not possible that if you take a course, you get a B plus or better, and you get a D plus or worse at the same time. It is either this or that, because these events have nothing in common. Now let me change the example. I hope that you're listening to me. The same example, you take the course, and then we have the sample space, which contains A, B plus B, and so on until F. Now, let's define the following two events. The event of getting a B plus or better. The event of getting a B plus or better, which contains B plus and A. So event E1 contains B plus and A. And the event of getting a B or a B plus. The event of getting a B or a B plus, which is event E2. So E2, again, E2 contains B and B plus. E1 contains B plus and A. Is it possible that these two events happen at the same time? Yes, it is possible. And this would happen if you get a B plus. If you finish the course, you check your grade, you find it's a B plus. It means E1 was satisfied and E2 was also satisfied, because these two events are not mutually exclusive. E1 and E2, as I try to explain now, are not mutually exclusive. If you try to get the intersection between them, that intersection has something in common, which is the grade B plus. Okay, one final example on set operations. Using the Venn diagram. So instead of having an example like this, which is explicit, so the events and the sample space are explicitly given, here we just have a Venn diagram. So we have event A, we have event B, both of them are in a sample space. Now, basically, we would like to get, if these are the events, we would like to get A intersection B. What is A intersection B? In common between them. A intersection B means contained in A and contained in B at the same time, which means the intersection, the common between the two. Now let me move to this example. A union B and then everything intersection C. The best thing is to do that on two steps. A union B. Let's get the set inside the bracket. Inside the bracket. A union B. What is A union B? This is A and this is B. So A union B would include everything here in A and B at the same time. So if you imagine stripes here, so the stripes would cover A and B, both. So if we have the event that covers A and B, let's do the intersection with C. This circle is C. So what's the intersection between AB union and C? Obviously, it's that shaded area. It's that shaded area, which is A union B first, and then intersection with C. Intersection, again, is common between the two. So between the C and between the A union B, which is only that green area. Finally, A intersection C, all complement. The complement is outside the bracket. A intersection C, complement. What's A intersection C? It's this white part here. That's event A, that's event C. A intersection C is the common between them, A and C. What's in A and in C, which means in between A and C? This is the white area, but this is not what we want. So the answer to the question is not this area here. The answer to the question is A intersection C complement. So it's the complement of this white area, which is the green. Do you see the green all around? That's the answer to A intersection C, all complement. And this finishes our lecture and this video. Thank you and see you next time. Assalamu alaikum wa rahmatullahi.